Hello everybody, welcome back to the final part of Homework 1, where we're going to be going over sum square error. Give me 1 second. Sorry, that was my granny. Anyways, so what we're going to be talking about in this part is sum of square error. So what sum of square error is, it's saying that the y from your model minus the actual y squared. And when we get into the coding part, what we notice is when we minimize this, we're going to basically get this to 0 when we minimize it. Now, the best way to do that is by optimizing it, where we take the partial derivative and set that to 0. Now, in our case, for the Antoine equation that we're talking about up here with our approximation vectors, ours get a little tricky. Because we're working with vectors, not just numbers. So, the sum square error still returns a scalar value, but in our actual meat and bones, now it becomes a sort of dot product, where our model is once again relating back to our basis vectors. So if we FOIL this, what ends up happening is we get our model vector squared plus our actual vector squared minus 2 y model y actual. So if we look at this piece by piece, so this y model squared, we're squaring this. So what's going to end up happening is we're going to get phi I, all that squared. So when we expand it, what's going to end up happening is we're going to get C1 times phi 1 times C2, well, C1 phi 1. We're also going to get C1 phi 1, C2 phi 2. And that's going to happen for all of them. So, this can be rewritten as a double summation. Ci, Cj, phi I, phi j. So that's what our model squared will look like. Now this is just magnitude squared, so we don't need to rewrite that out. But for this, it's going to happen to our y model vector, our y vector, that's going to look like is 2 psi summation ci phi I dot product of y. So that's what that's going to look like. So, that followed out. Now, we have n number of constants. So, what happens is when we take the partial derivative of our SSE, or sum squared error, with respect to each constant, I'm going to do CK, just so there's no confusion. And we're going to set that to 0. So now, let's go through this term by term. So, starting with our y model squared, so this one here. Let's start with here. So, there are 3 different cases we have to think about. So, when I equals j, and they both equal k. When that happens, the inside of here is going to look like this. So we see k squared multiplied by phi k squared. And then when you take the derivative of that, you are left with 2 phi k squared times ck. And that's your partial derivative for that term. Next term, or next case we have to look at is when I equals k, but j does not equal k. When that happens, we have ck times cj times phi k times phi j. When that happens, we take the derivative of that. We are left with cj phi k dot product phi j. Get all this. Now, we also got to look at when I does not equal k, but j does equal k. When that happens, it's the same thing up here. We've got ck. However, instead of cj, it's ci. And then you take the derivative of that, ci phi k phi j. Or phi I. However, if you notice, j is 1 all the way till n. I is also 1 all the way till n. So when we go down to rewrite this all together, these aren't going to be separated. These are just going to be 2 times the sum of ci phi I dot product of phi j. And of course, the last case you have to talk about is when I does not equal k and j does not equal k. ci, cj, phi I, phi j. Now when you take the derivative of that, all that goes to 0. Because in respects to cj, these are constant. So, our partial derivative of e squared with respects to Cj, or Ck, I mean, is so far equal to 2 Ck phi k squared plus 2 multiplied by Ci phi I phi k. Alright. So we got our first term handled. Now if we go back up here, our y actual squared. Now, those are all constants, so we take the derivative, 0. Don't gotta worry about it. Now we gotta worry about the last one here, though. Around here, we erase the plus, because that was negative. And let's look here. So, you only have to worry about I here. So we have two cases to worry about. When I equals k, we got Ck phi k dot product with y actual. And when you take the derivative of that, you're left with just the phi k y. And then when I does not equal k, just Ci phi I, y is again constant in respects to Ck, so therefore it's just 0. So this is the only term we got to worry about for this one. Go down here, so minus 2 the phi k the dot product of y actual. So that is where we're at with that one. Okay. Y actual. So this all ends up having to go to 0. So to get that to 0, we got to do so what we're going to do from here is, if you notice here, we got k here, we got I here. However, because of our statement up here, where we said I and j do not equal k, we come down here and we have to say I does not equal k again. Excuse me. Got my heartburn medicine. Anyways, so what that means is we can combine these two and get rid of this I does not equal k. So we go here, say 2 sigma Ci phi I phi k. Now, it's from 1 all the way to n. Instead of 1 to k, and then the k plus 1 to 1. Or k plus 1 to the n. This out. Okay. Now, if you need a better explanation for that, or more clear, think about it like this. So this sigma says from C1 times phi1 phi k plus C2 phi 2 phi k plus so on so on. However, it excludes when I is equal to k. So, if this did not, so another way to rewrite that would be add all the way from I to k, but at the end, subtract the c when I is k. So that's another way to rewrite that. When I does not equal k, you add them all together as if k was a part of it, but you subtract it at the end. So that's why when you add it, here, these two are going to cancel out. And then so will the 2's while I'm at it. So we'll get rid of the 2's. So that's why this doesn't exist anymore. And why this no longer applies down here to this term. Now doing some algebra, what I can do is I'm going to send this over to the other side of the equation where it equals 0. So now we have a bona fide equation of Ci phi k, both of them vectors, equal to phi k y. That dot product. So, just like we did with the approximation vectors down towards the bottom somewhere. Yeah. So like just like down here where our dot product can be rewritten in matrix multiplication terms as the transpose of 1 multiplied by the other vector. So, got the dot product here, so I can rewrite that as the transpose of phi k multiplied by our vector y. And then same deal over here, where I can say the sum of Ci times phi I transposed to phi k. So now when we rewrite it, we get all of our phi's, phi2, phi3, multiplied against all of our design matrix. Because keep in mind, our k is going to repeat for all of our different indexes. So that's going to repeat like that. And then we also have our coefficient matrix, our C1, C2, C3. Equal to, once again, this will be now a transpose, so that'll be a row matrix. This is our phi 1, phi 2, our phi 3, and then our column vector of our known values. Now, if you notice something, look at this equation, memorize it. Let's go back to the bottom of ours. Have our transpose of our design matrix times our knowns. Our transpose times our knowns. Our transpose times our design matrix. Transpose times our design matrix multiplied by our coefficients. So, what this is saying is that by using sum squared error method up here, it'll give us the same result as the approximation vectors. So to show that, what we're going to do is we're going to go back to our script we were working on earlier. We're going to import minimize. So from scipy.optimize, import minimize. And what we're going to do is we're going to make a new problem. So what I'm going to do is x data is equal to np len space. And let's go 0 to 10 with 11 data points. So when we do x data, we should get 0 through 10. And let's make our function what do we want to do with it? Say x squared minus 5x. Oh, let's do negative x data squared. So we get a upside down parabola. And let's add, say, 5 times x data. And let's go up by 3. So if you do fig equals go dot figure, layout, default layout, raw data equals go dot scatter, x equals x data, y equals y data. So, as you can see here, starting at 0, we have this curve, like that. So, from here, what we're going to do is we're going to set up a sum squared error function. We're going to input a vector, which will be our coefficient vector, or the coefficient column vector, that we are discussing right here. So this is what that phi is going to represent. So, do here, we're going to split that, ABC, and we're going to return a times x squared plus b times x plus c. Data. And then this is going to be our y approximated. Oh, let's do y estimate. Then what we're going to do is we're going to return the sum of all those errors. So we go here, do a minus, y estimate minus y data. I want to square that. So So now if we go to minimize, plug in our function, and for our x naught, let's do just ones. So if we run that, got true. What minimize gave us was -1, 5, 3. Up here, -1, 5, 3. So that's correct. Now, let's do our, like up here we did the matrix form for that. Up here, except now we're going to have it fit to here. So, if you want to think about it like this, where you have ax squared plus bx plus c equal to y, you already got somewhat of a linear form. You got one term here, this is your phi 1, your phi 2, and your phi 3. Then this is your known vector, or your v vector that we've been calling it for this assignment. So, go back into here. Now let's set that up. So for here, I'm going to say res that. And here, a vector is going to be npc through x data squared x data, and then x, well, no, mp1's like x data. Our b vector here is going to just be our y data. So now if I do alg.solve a.transpose a.transpose b. If I do that, what do we get? -1, 5, 3. -1, 5, 3. So as you can see, both of them give the same answer. Now, say, for example, up here, instead of being perfectly fit data, say np.random random, let's do x data dots. That's how you do it. Oh well. Hold on. Let me see if I can remember how to do random. Is this the one? If I do that, do x data dots. Let's do low, let's say -5. High. You see it's a little less clear-cut. So if I run that, I display res.x, run that, notice that we are still getting very close answers. even though the error is... there is some error. The reason there is some error between these is that the transformations we're doing, for example here, by squaring the x data is there, we're also transforming the errors in there. So if we were to, for example, reduce the error, error a little less great. So you can still see a very strong shape. Notice 3916, and there isn't a discrepancy till what is that? The 1, 2, 3, 4, 5, 6, 7th variable or 7th decimal. But if there is no error, we get the same exact error, or same exact answer. Now what you're noticing here is if I don't do the x, the reason why is because after so many decimal points, there's round-off errors. So like for example right here, since these are exact, that should technically be 0. But since computers use something called float approximation, there's always going to be that little bit of error as you get to those smaller decimal points. But like say for up here, like you notice like, hey, there's a little bit error here. There's some, maybe some error down here, although it might be slight. But if we were to do it for up here, find SSE A, B, C equals B, Y new equals A minus B over df.temp plus C, to return p.sum y new minus y. I'm going to square that. And then just minimize SSE ant. For our initial guesses, let's just do 1s. Why not? Run that. Y is not defined. Yep. df dot np dot log df dot pf. The reason that has to be a log is because this is not raised using np dot expression, right? np dot exponential. So if I run that, it's true. But notice, got 2.351, or it'll be 23.51. We got 23.55. A small bit of error. No slight difference here. 4080 instead of 4044, and 3634. So just like down here, if it was perfect data, they'd be the same. But instead of getting that perfect, there's error within the data set causing that discrepancy. But, like here, if the data is perfect, it will be the same as using approximation vectors. However, if there is error, when you go to transform those vectors, so say take the log of it, you're going to have a lot more error. And just to point out how big those transformations come in, the play, do that. See, that's almost not even a parabola anymore. if you run that, you're still getting pretty close because we're not using transforming that. If we're making a transformation like up here, we get a lot bigger discrepancy. But because there is no real transformation down here, our answers are still coming out the same. So, do like 100. That's definitely not a parabola no more. Run that. Run that. Now, well, it failed because error's too much. So let me just do like, let me see if 20 is too much for it. Yeah, 20 is too much. If I try running that. Yeah, so even when it fails, it's still giving us the same answers. So it didn't converge, but it's still giving us the same answer because we're not transforming anything in here. However, up here we're transforming it to the, by taking the log, we're also transforming the error, causing those differences. So with that, that's been homework 1. I hope you guys enjoyed. You learned something. Hopefully you learned something. But it was fun. I hope you guys had fun. And I will see you guys next time.